It's a privilege to be here today to talk about our journey towards productizing SparkML in a context which is maybe a bit different than usual, which is real-time bidding. We will, in this presentation, we'll try to go over a few of the lessons learned in the process. We started this very early, in the early years of Spark, but now we're running full-fledged production for almost 2 years now, using SparkML, and we'll present a few problems that we faced along the way. Some solutions might not be the unique solutions, but we'll share those that we found. And we'll end up with a demo. Javier will be doing a demo of the system and to try to show some examples of the concepts we'll be presenting today. So Dataxu is a Boston company, and the main purpose is it has a platform that helps marketers run effective programmatic campaigns with a focus on TV. It's about making decisions, a ton of decisions, as we'll see, on each second, on which ads to show to whom at which time, and that's at the core, the automatic decision. So what is this real-time ad bidding? Some of you might be familiar, but each time you're browsing, if you're watching a TV episode, or if you're playing a game on your phone, or just browsing on your tablet, there's a ton of ad opportunities to be shown, from banners to commercials between episodes and different opportunities. And there are ad exchanges that host these ad auctions. Each time, suppose you go through a web page, and as the web page loads, there's an auction happening right there at that very moment. And ad exchanges host those auctions, and there are several bidders. Dataxu is among those bidders, and the decisions that Dataxu needs to make is, of course, well, which ad to show for that ad opportunity, how much to bid for that ad opportunity, and of course, there's machine learning behind these decisions. If you bid too high, you're going to be overpaying the price of the ad. If you bid too low, then chances are you won't spend the campaign budget you were planning to spend at a particular pace. So that's a problem too. We need to pick, the right amount for the right user, showing the right ad at the right time, the right location, lots of parameters. And this is where ML fits in. The Dataxu's mission is to make marketing smarter through data science, and I could talk a lot about the amazing features which we're very proud of Dataxu's platform, and you should check them out. But today we're going to talk about the machine learning behind Dataxu, and of course, in particular, the ML being applied to bidding models. So what is the input data? Of course, the input data is past bids, past losses, wins, attributions, which are events that happen after the end user witnesses an ad and then performs a positive action, like visiting a website or buying a product. Those are attributions. Those will effectively be the positive instances on our machine learning data sets. And with all this data, we construct models which are specific for each campaign, and ship those models to what we call the real-time system, which is responsible for doing these bids and performing these bids real fast. To give you a sense of scale, we process 2 petabytes of bid information daily. In each second, we process 3 million, we make 3 million ad decisions. That is, for each incoming bid request, we need to decide what's the best ad, on behalf of which of our advertisers, how much to pay for those ads. And this happens 3 million times a second. So it's a pretty complex problem, and we were wondering whether Spark could do the job. Of course, it needs to run 24/7, all continents. These bidding machines are spread across the world to reduce latency. And we train thousands of machine learning models per day. So what are the desired features of such a system, such a machine learning system? Of course, it needs to be highly predictive. It needs to be able to discriminate those good opportunities from those bad opportunities, right? We need to bid the right amount. It needs to be fast to bid. In less of a millisecond, we need to come up with a bid, and that's extremely low latency. We want to do more with less. We want to optimize our clusters. We want to optimize every single process of machine learning system. It can go down, obviously. We constantly need to update models with new trends in the market and new opportunities being explored. And of course, it needs to run in an unattended fashion. We cannot have data scientists craft specific models, spend a week on these data sets, and just deploy into production. We sometimes do that, but we cannot have that as a default behavior. It needs to run in an unattended fashion, and of course, for that reason, these models need to be self-tuned. On the other hand, they also need to be transparent. Transparent in two senses. The first sense, these models, we need to understand why these models are behaving the way they are behaving, sometimes for our own sake, and sometimes because our customers ask us, why are we bidding in a certain way? And we always have a good explanation for this because our models are transparent. And the second aspect for which we want to be transparent is, we want to compare using these machine learning models against not using some sort of default behavior or default bidding strategy, see how much we win from using these ML models. And occasionally, some customers want to bring their own algorithm, crunch their own data, just ship their own algorithm into the platform, and we want to be able to do that. We were wondering, whether Spark was doing this. And let me give you a bit of history. 9 years ago, we had a custom Hadoop job built in-house that in a single pass, it traversed the whole data set, which interleaved data from different campaigns. And on the fly, in that single pass, it created models for each of the campaigns. And then these models were shipped at bid time. Then we were starting to ask our questions, can we use, this was 4 years ago, can we use Spark? Is it fast enough? Is it thread safe? Does it use too much memory? Because all these in-house products we built obviously were very custom and very specific, and they were very highly tuned and very performant. Is it expensive to train? Maybe we can do different algorithms than the one that we were using, and in some campaigns those algorithms might perform better or no. Those kind of questions were the ones that we were having. Can we ship out of the box ML algorithms? And do these SparkML models actually work well with our data compared to the solution we had before? And the spoiler alert, the answer to all these questions is yes. And let me go through a few of the problems we had. The first problem was the data partitioning. In the Hadoop world, where we on the fly trained several models in memory for the different campaigns, we didn't have to reorder our data so that each model would have its own data set. That is a requirement in Spark. SparkML, you need to submit a single data frame or data set to the training job to get a model, right? So we had to somehow partition all this data by campaign and separate it, split it. And of course, when one tries to do this and the data is uneven or skewed, and we saw a great presentation today from Yelp on how to deal with the skewness, we do a little bit of that. In particular, for this problem of data partitioning, we first do a sample pass on the data sets to find the relative sizes of each of the campaigns to build a distribution. With that distribution, then we can allocate more resources to the larger campaigns and less resources to the smaller campaigns. We do this by creating artificial partitions or shards. You know, large campaigns will have more artificial partitions, and smaller campaigns will have less of those. So in a quick sample pass, we get an estimate of the distribution. In a second pass, we do the partition by, so to speak, partitioning of the data set. Obviously, we need to do this because everyone probably here has faced some issue with skew one time or another. If you work with Spark or Hadoop or all these big data systems, the chances are if you don't do this kind of strategy, you will have one executor with a larger campaign trying to crunch all the data, and all the other executors or reducers, you know, finish very quickly. And this, of course, creates idle resources on our clusters. The second problem we had, and we share a lot of these problems with the earlier presentation by Uber, is that the Spark models were really not ready for a low latency bidding setting. Spark is great at constructing the predictions given an entire data set. So if you receive an entire data set, you will get predictions for all the rows in your data set. But how about, you know, the setting or the scenario we have at real-time bidding, in which we have an incoming bid request, and immediately, in less of a millisecond, we need to respond with a bid. In this case, we don't have the luxury of creating a Spark context. We don't have the luxury of running a Spark job, or even the streaming, Spark streaming. So because of the low latency. So at bid times, things are different. Well, what we did is something similar to what the Uber team did that was mentioning this morning, which is to expand Spark with this concept of raw models. These raw models are models capable of providing predictions given a single row of data without having Spark jobs run to create those. Just reusing all what Spark has to give in terms of the lower level models. So we extended Spark. We created our own pipelines, our own estimators, our own transformers, which are basically just wrappers around Spark estimators, transformers, and pipelines. And in most cases, it was just these wrappers would only delegate to the right Spark class. We didn't have to kind of re-implement these transformers, except for one, I think, which is a SQL transformer. Except for that one, we could just delegate to the right Spark class, and these wrappers worked out of the box. And it isn't hard to maintain. Some of this stuff is open source. The third problem we faced was the categorical encoding. Of course, if you've done machine learning with Spark, and you have a lot of categorical data, like we do at real-time bidding, you need to somehow transform these categories into numbers, right? Spark models work out of numbers, out of vectors. So we need to vectorize these categorical features. You could run a bunch of string indexing jobs and do the job. However, we found that this is slow and sometimes even memory prohibiting, because if you have a column or an attribute whose cardinality is very large, then we will obviously build a dictionary of the category value and its index. And if this dictionary is large enough and this dictionary gets sent to the driver can run out of memory very quickly. So what we did is we used the ideas of Metwali, Agarwal, and Abadi to try to, on the fly, for several columns or attributes at the same time, try to compute, try to get the top K most frequent values for each category in a single pass. And with that, we construct a dictionary of index element. Of course, this has its disadvantages because there's always going to be a long tail of categories that won't get mapped. But we found that the advantages of this outweighed the performance reduction. This is also open source on Dataxu's GitHub. The fourth problem we found that it was actually, after we did all of this and we managed to get Spark to work, it was expensive to train, and we were running one campaign at a time. We observed that if we that some campaigns actually took hours, some a few minutes. Some of the training was I/O bound, some was CPO bound. We observed cluster idleness between jobs. And so the solutions we found was to launch in parallel smart batches of jobs. We submit a bunch of training jobs at the same time. By doing that, the I/O intensive and CPU intensive bits of the jobs would interleave and maximize the usage of the cluster. We didn't use the max resource allocation from Spark, and we carefully overbooked the cluster resources, and this actually did the trick. We got a 60% cheaper cluster than the one we used with a one-pass Hadoop method. And these algorithms that we were using for this particular 60% test were random forests. So, it's algorithms that require a few passes on the data. So it was a good improvement. Of course, once you have the system ready and we have models that we can ship into low latency bidding environment, how do we switch from a system that's stable and running in production for several years? We did this in stages. The first stage was to do a decorated approach in which we injected the Spark model inside our traditional or legacy bidding model. And for some of the users, we started using the new model. And we pulsed that using the standard data science. And for example, on that day, I think it's the 7th of September, we parsed that model, and we saw that there was a big increase in ATR. ATR is the attribution through rate, which is the number of attributions we get per impression, or per ad shown. So it was a good, for this particular campaign, it was a huge success. And that was first stage. The second stage was, well, this is only a portion of the bid requests that start to receive the new model. What would happen if we completely replaced the bidding machine to use a Spark model? We faced latency, throughput issues, garbage collection issues, who knows? So the second stage we did was replace the whole system for one machine. And we did notice some issues there in latency that we didn't manage to reproduce on our simulations. And we solved those through doing some profiling on YourKit and profilers like that. We realized there were a few hotspots in the way we created these Spark wrappers, and solved those by tuning those particular bits. After we tuned those particular bits, the latency was as the expected. And of course, once we validated that, we did the full switch. We replaced all the bidding machines to use the Spark models. And did everything go as planned? Well, yes and no, not exactly. For the latency situation, I already explained that we did some profiling. But when we deployed the new Spark models to all the hundreds of bidding machines, we saw that these models were actually stored in S3, and all of these machines were grabbing the models from S3. We actually faced a throughput issue upon deploy. This was immediate, so it didn't have any real impact, but something that we didn't foresee. So we had to roll back. We had to implement additional retry strategies beyond those existing in the S3 client libraries already, and some other strategies. And with that, we managed to solve this particular problem. So what about self-tuning and unattended operation? This seems to be the tricky bit. And for addressing some of these problems, we approached to use what is called a blackboard pattern. This is not the blackboard pattern in the sense of AI. For those of you that have a background in AI, this is a blackboard pattern in terms of software engineering. Basically a decoupled producer-consumer pattern, where the blackboard has the latest artifacts of the different sub-products of, or you know, as intermediate artifacts of our training process. And each process will grab those latest artifacts from the blackboard and put the results back in the blackboard. This is because most of our ML system is based on getting the most recent data you can for a particular thing. It has lots of advantages because, you know, if one process fails, you can still have the latest data from the previous process, and we make sure that all these processes are compatible with previous versions of the data so that we end up with a very robust system. And we use S3 as the blackboard. You know, it's just, this was as a decision out of simplicity, really. S3 it can be seen as a file system, and a file system abstraction is easy to abstract, and it's easy to test. So when we run on our local machines and when we run the system, instead of using the S3, we use our local file systems, and everything works. We can understand exactly what's going on. We could obviously use more sophisticated more sophisticated technologies, but S3 was simple, and that's why we chose it. Of course, we run into this issue of throughput, but that was solved, and even AWS has strategies to deal with this problem. In a nutshell, we have event data as input. The trainer builds models on these, on top of this data. It creates those models, stores them with the blackboard. Then we have a model selector and calibrator that will actually calibrate these models and store those calibrations back in the blackboard. For example, we train several different kinds of models for each of our campaigns, and the model selector selects the best one that applies for each campaign. Those calibrations, and along with other processes for insights, things that are not straight machine learning, are also put into a blackboard. And with all this information, we build a manifest. This manifest, and Javier is going to show in detail what this manifest is about, is a set of steps that each bid request needs to undergo upon bidding. You know, it needs to select for each particular bid request, for each particular campaign. It needs to be well-defined what are the steps that we need to carry out, which model we're going to use, what transformations are we going to make for each of our bids. And we store this bidding manifests back to S3. So the bidding machines actually pick up those manifests. When a bid request comes in, it knows exactly what to do in a declarative fashion. So it's very clear, and we are transparent in this sense. So exactly, what about transparency? This is an example of a manifest, but I'll leave Javier to show that because he'll do that in a very detailed fashion. Of course, the other sense of transparency, which is we need to understand whether the models building with a classifier work better than the models, you know, just random bidding or, you know, fixed bidding. And for that, we create panels, we do A/B tests, and we get a sense of how well these models are doing. This is beyond metrics like AOC and ROC, which are on the training side of the process. But these are actually empirical results. What happened, you know, how many people actually converted or bought products after showing an ad is run by these A/B tests. Is it easy to deploy new algorithms? It took us 2 days, just 2 days, to deploy a standard ML pipeline that a Dataxu customer wanted to plug in. So it's definitely a success of this Blackboard design. So with this, I'd like to give it to Javier, who's going to run the demo and explain all of this in an example, in a narrowed down example. So please welcome Javier.
Okay. Okay, so thanks, Maximo. So as Maximo said, at Dataxu will run this real-time decision engine, which bids on millions of bid requests and decide how much to bid on this bid request on behalf of our advertisers. So we fit the real-time decision engine with machine learning classifiers that we train on our infrastructure, which runs offline and is built on top of SparkML. So these two components, the offline machine learning infrastructure and the real-time decision engine, are almost fully decoupled. As Maximo mentioned, we use the Blackboard pattern, and they only communicate via a manifest that we create, which is just a file that we drop in our Blackboard, and the decision engine is polling that Blackboard to get the latest manifest and update itself. And this process is constantly running, and the decision engine is constantly updating itself. So for the purpose of this demo, what I did is I'm running these three components: the real-time decision engine, the offline machine learning infrastructure, and the Blackboard in my local file system. And of course, I'm running a reduced version of our system for which I only created 4 campaigns that we want to try. I call them awesome shoes, awesome cars, awesome bags, and awesome shirts. Okay, so of course we have some parameters here, like the base bid, like kind of the bid value on top of which we want to optimize, and some are metadata that is needed in order to create our manifests. Okay, so you can see in my Blackboard, which is just a folder here, that it's almost empty. We just have an initial manifest that I created here, which is empty because we have no data for. First time we run our infrastructure, and before we have any data, we have nothing to put in our manifest. Okay, so with this, let me run this Java process here in my terminal. That what we'll do is we'll simulate the real-time decision engine. And of course, as Maximo mentioned, we are in production, we are bidding on 3 million of bid requests a second. But for the purpose of this demo, I will only be bidding on 1 bid request every 5 seconds. So run this, it's simulating the decision engine, it's loading the needed metadata, and you can see that every 5 seconds I'll receive a new bid request, and I'll bid on behalf of my 4 campaigns. And as I have no data, I have nothing to optimize on top of. I'll just bidding a default value for all of them. Okay, so as I said, what we need to do in order to inform our real-time decision engine on what bidding approach to take for different campaigns, I need to create a manifest and drop that in my Blackboard. So I have this notebook here, which has some utilities that are handy for doing this. So I'll just run this cell here, which creates a new manifest, and I can show you here in my Blackboard that indeed it created a new manifest. So in this case, as the infrastructure now knows about the campaigns that we created, but it still has no machine learning classifiers to use. It's just saying that for each of our campaigns, we just want to use an identity model, nothing strange there, and use the flight-based bid, which is the configured-based bid here for the campaign, to bid. Just bid flat that amount. And if we go back to our decision engine, we can now see that for the different campaigns, we are bidding a different amount, which is exactly the configured amount that we had. So after we are running this and we are collecting new data, what we can do is we can define machine learning pipelines that we can feed on past data, and that way, sorry, this is hidden. That way, use machine learning classifiers to optimize the bid on production. So defining this is just as simple as defining any SparkML pipeline here. I'm just adding three stages here: a SQL transformer, which is selecting some features, doing some feature extraction. I'm adding a top K stage, and last a vector assembler, because our random forest classifier needs our features in a vector in order to train. So if I run this, you can see that I just create one object, a Spark dataset pipeline here. And now with this pipeline defined, what we can do is feed it on past data we collected in our real-time decision engine. So of course, for the purpose of this demo, I won't have time to train these classifiers, but what I did is I pre-trained one classifier for each of these campaigns. And each time that we train, what we do is we collect some metrics for the different classifiers that we train, and again, we store that in the Blackboard so we can pick it up later to choose what model to deploy to production. So these metrics are just a CSV file which contain what campaign we train the classifier for, some metrics about the classifier, and where is the classifier stored in our Blackboard. So in this case, what I do, I'll show you, I have my CSV here. It's not actually CSV because we use this as a separator, but it's okay. What I do is I'll drop this file in my Blackboard, and I'll show you that I had some bootstrap stuff here because our infrastructure would fail if there's nothing there. I just add this, and what I can do now is create a new manifest. So this new manifest will pick up these metrics and pick the best classifier that we can get from our Blackboard for each of our campaigns. So in this case, you see we are no longer doing that fixed bid stuff. We are actually using a campaign-specific classifier for each of our campaigns and doing some bit modifier stuff. Again, if we go to our decision engine, it picked the latest stuff from the Blackboard, it updated itself, and it's now using the different classifiers that we have for performing real-time decisions in the real-time decision engine. So what's happening there, as Maximo mentioned, is that we have these raw models instead of our dataset pipeline models, which are the things that Spark generates each time that we feed a pipeline. And so each time that we feed a model, you can see that we store in our Blackboard two things here, two serialized things. One thing is the dataset model, which is what Spark generates, and the other thing is the raw model, which is what our real-time decision engine loads for making real-time decisions. So I can show you here that I can deserialize my raw model from my Blackboard, and this is exactly what the real-time decision engine is doing, and this triggers no Spark job because there's no Spark context here. I can show you that it has exactly the same stages that we define. A SQL transformer, a top K vector assembler, and last the random forest. So what I'll do here is load 3 transactions in memory and show you that we are able to produce like timely predictions. In this case, they are taking some few milliseconds, but of course, I'm running this in my local machine, and some other stuff is running here. When we run this in the actual decision engine, it takes less than a millisecond, as Maximo mentioned. Okay, so next thing I want to show is that once we have this machine learning infrastructure, it's a data scientist's best wish to be able to perform measurable A/B tests on experiments in production. So for doing this, as Maximo said, we do paneling of our campaigns. We support 1,000 different panels, and these panels are based on the user that will be watching the actual ad that we serve. And so we bucket the user in 1,000 buckets, and we can say for different buckets, do use different bidding approaches. So in this case, I'm introducing a manifest change, which is kind of an experiment, and I'm saying that for my awesome shirts campaign, I want to use the awesome shoes model, because I think that can help. So I'll run this, and this will create, again, an entry in my Blackboard and shows exactly the JSON that I created. And if, again, I recreate my manifest, I'll see that a new update is done here, and my awesome shirts is now paneled. And also, we have this raw here, not the merged manifest, but the raw. In this case, it will not be paneled, and this is because we want to be transparent. And in case something is happening in a campaign, we want to know if that's caused by our unattended and automatic infrastructure, or caused by an experiment being run by our data scientists. Okay, so I can show you now that the decision engine updated itself, and probably we can see that for some of our awesome shirts stuff, we are using our awesome shoes model as expected. Okay, so last thing I want to show you, let me kill this process, the real-time decision engine, is how to analyze the bids. And I'm sorry I had pre-run this because I was hitting some weird issue when trying to load the CSV. So I was logging our bids, same as we do in production, into a file, into a CSV file that is this one here, bids.csv. And if I load that, you can see that we have the request ID, how much we bid, what approach we took to bidding, and the panel to which the bid request belonged. So now we can plot our bid request over time. See that initially we were doing fixed bid because we had no machine learning classifier. Then we were doing this using the classifier. And after all, we run our experiment. So what I'm doing here is I'm splitting the bids into exposed and controlled for my experiment. And I can see that here, after the experiment kicked in, for my awesome shirts and my awesome shoes campaigns, in the case of the exposed users, we are always bidding almost the same, and this is because the configured base bid is a bit different, slightly different. But we are always taking the same approach because we are using the same machine learning classifiers. On the other hand, for the control, those users that were not exposed to my experiment, we are still doing very different, taking very different path when bidding, and this way one can analyze if my experiments are working better than the automated infrastructure or not. Okay, so that's it for the demo, and we have one last slide with some benefits and some lessons that we learned. So of course, as Maximo mentioned, we got better overall performance. We are training quicker and using less resources than we were doing before. We have less code because Spark APIs are good for that. I would say better than the Hadoop stuff. And some of the lessons that we learned is that Spark, of course, can be used for serious production system, and we are running this 24/7 on 5 continents, unattended every day for 2 years now with no major issues. Some tweaks are needed for the SparkML library, but you still can use the machine learning algorithms that are produced by the community and leverage that to make real-time decisions in a production environment. And also, there is no test like a full live test, because as Maximo mentioned, we run many of our simulations, but after doing so, when we try to ship our full stuff to production, we still hit some issues, and you would only get that when you're running on the scale that you're running on production. You will probably never be able to simulate that same scale on a different environment, and hence see the potential issues that you might reach or you might hit when going full live to production. And that's it. Thank you, and we are open to taking questions.
Yeah, so what are the metrics you're maximizing for within your kind of scenario? Is it click-through rate on the ad? Is it budget on the ad? Is it exposure per budget?
It depends. So
Okay.
we have depends on the campaign. The campaign might have different objectives. It could be action through rate, click-through rate. It could be exposure to a particular audience. It could be a distribution. It's decided by the end user picks or the platform user picks the algorithm that matches the objective that they want for the campaign.
Okay, I think we'll have to move the rest of the questions to the back of the room. Please give Javier and Maximo a warm round of applause. Thank you guys very much.